Okay, let's talk a little bit about how we handle unsigned and signed integers in the C language, which we'll be using in our first homework assignment. So as I mentioned in the previous video, the numbers that we can represent in both unsigned and 2's complement notation have maximum and minimums. And what we have here is a table that shows what those maximum and minimum numbers are for various sizes of the word. So W of 8, 16, 32, and 64. And you can see the basic property is that the range of the 2's complement numbers is pretty much symmetric. It turns out there's one more negative number than positive numbers, but that's pretty close. And in the case of unsigned numbers, the maximum number we can represent is about twice the size of the maximum 2's complement positive. C provides support for unsigned and signed numbers in a file called limits.h. .h files are header files, and they can be included in our own code by statements such as the one above. You'll see these come up in some of the sample code that we'll give you for the homework assignments. But in limits.h, for example, we have some constants that are pre-declared for us for the various maximum and minimum values for both standard word size and the long integers. And these values are platform specific. So we'll be using limits.h that's on a Linux system. Of course, if you're on a 64-bit Linux machine, things will be more in the 64-bit values. If you're on an older machine, you might see the 32-bit values. Okay, so in C, constants are by default considered to be signed integers. So a number, if we declare an int, it's a signed integer. If we want it to be unsigned, we have to explicitly say so. We can also, when we just write a number to say that we mean it to be represented as an unsigned integer, we can just add a capital U to the end of it. So numbers such as these are unsigned. Okay, so in the C language, again, int is for integer, and that means a signed integer. If we want unsigned, we use just the word unsigned. And then we can cast back and forth between these numbers. So we can take an unsigned integer, cast it as an integer, as a signed integer, and assign it to a regular integer variable, and vice versa. Implicit casting also occurs, so we don't have to put the explicit way we want the number interpreted in parentheses. And this happens both in assignments and in function calls when we use these variables as arguments to a function. So here we have an unsigned value being assigned to a signed value being assigned to an unsigned value. Now, what happens in the compiler when this goes on is it basically will figure out how to move that number, not actually move it, but reinterpret it as the corresponding unsigned or signed integer. Okay, but let's take a look in a little bit more detail on what actually happens here. And we're going to look at a set of examples. The key thing to remember is the bits are actually unchanged. We're just going to interpret them differently. Okay, so if you mix unsigned and signed values in a single expression, then signed values get implicitly cast to unsigned. So unsigned dominates, if you will. So let's take a look at what happens here in some examples. Suppose I have the constant 0, which is a signed value, and the constant 0u, an unsigned value. Well, these values are exactly the same, but they're both evaluated as if they were unsigned. In other words, this signed 0 is being reinterpreted as an unsigned number. Fortunately, 0 is all the bits are 0 in either case, so that's pretty straightforward to do. Let's take a look at the next one. -1 unsigned, I'm sorry, -1 signed and 0 signed. Well, in this case, both numbers are signed, so we will do the evaluation as signed numbers, and we would expect, in fact, the -1 to be less than interpreted as being less than the 0. In terms of the bit patterns here, though, remember the -1 is all ones. The 0 is all 0. but it's going to be interpreted as a signed value, so that first bit of the representation of -1 has that high negative weight, which will make it less than 0. Okay, now if instead we compare the -1 to a unsigned 0 in the next line, that's a little different, because now we're going to reinterpret the -1 as an unsigned value. Well, all ones reinterpreted as an unsigned value is a huge number, because we lost that negative weight of that first most significant bit. So now we have a large number, and it's going to come out as being greater than. So look at that. If just because one of the constants is interpreted as an unsigned number, we get a totally different result, even though we might think we're comparing the same values. But that's just because of how the numbers are being interpreted. And C has this convention of converting everything to unsigned interpretation if we mix the two types. Okay, let's take a look at a different example in the next line. We're using here a large positive number as a signed integer and comparing it against a very small negative number. And here again, both are signed values. We'll interpret them as signed, and of course that large positive is greater. Now again, if one of them is interpreted in fact as unsigned, what happens? Well, that big negative number is also going to be converted to unsigned, and what does it become? It becomes an even bigger positive number. So now the comparison will say that the number on the left, which looks like a positive number, is less than this supposedly negative number. But this negative number was reinterpreted as an unsigned value and turned into a big positive number. Okay, next example, -1 against -2, both signed. We would expect the -1 to be greater than the -2. In the next example, a -1 cast as unsigned, again yields a huge positive number. It is going to be greater than the -2. So in this case, it happens to work out that we get the same result, but again, that's only because of the interpretation. Okay, let's take a look at the last two lines. Here we have a large positive signed number compared against a large positive unsigned number. What will happen here is that that number on the left will be converted to unsigned as well. Will still be a relatively large positive number and still smaller than the one on the right. So here we would expect less than unsigned. Now, if instead we cast that unsigned number as an integer first, reinterpret the bits, well, that number turns out is just large enough to have that most significant bit set to 1. So when we interpret it as an integer, it's going to look like a negative number. And in this case, we would expect the opposite result when we compare them as signed values.